Before July 2015, Pluto was a smudge, not a world, not a surface, not a place with geology or weather or anything that distinguished it from the billions of other points of light in the sky that we have never visited and never closely seen. The best images ever taken of Pluto from Earth, including images from the Hubble Space Telescope, which can resolve detail that ground-based telescopes cannot, showed a blurry disk a few pixels across with hints of brightness variation but no discernible features. No mountains, no plains, no atmosphere visible as structure, just a suggestion of non-uniformity in something too small and too far away to see properly. For 85 years after Clyde Tombaugh discovered Pluto in February 1930 by comparing photographic plates taken on different nights and noticing a point of light that moved, for 85 years of increasingly sophisticated astronomy, increasingly powerful telescopes, increasingly refined orbital mechanics, nobody knew what Pluto looked like. Nobody knew what was there. Then New Horizons arrived. The spacecraft launched in January 2006. It travelled for 9.5 years. On July 14, 2015, it made its closest approach to Pluto, passing within approximately 12,500 kilometers of the surface, closer than the distance between New York and Tokyo. And in the hours around that closest approach, it collected data at the maximum rate its instruments could manage, storing everything in its onboard memory because the antenna needed to be pointed at Pluto for science rather than at Earth for communication. The images and data that came back over the following 16 months of transmission changed the scientific understanding of Pluto in every specific way it could be changed. Everything the scientific community thought it knew about what Pluto should be, cold, dead, simple, geologically frozen since the early solar system, turned out to be wrong. Not slightly wrong, not wrong in marginal ways requiring modest model adjustments, wrong in the ways that produce a decade of new papers, new debates, new theoretical frameworks, ongoing reanalysis of data, still yielding discoveries almost 10 years after the flyby. Tonight we are going to go through what New Horizons found, not the summary version, not the 3-sentence explanation, the actual physics and geology and atmospheric science that the images and instruments revealed, the specific discoveries that changed our understanding of what Pluto is and what small icy worlds in the outer solar system can be. Before we begin, if you put this on because the night is long and you need something to settle into, stay. Pluto is stranger than almost anyone knows. Let us start with the most fundamental fact about Pluto that New Horizons established, a fact whose implications extend far beyond Pluto itself to how we think about the outer solar system as a whole. Pluto is geologically active. Not was active billions of years ago, is active now, in the geological present. This should not be possible by any prior theoretical expectation. Pluto has a diameter of approximately 2,377 kilometers, smaller than Earth's moon. Its mass is approximately 0.18% of Earth's mass. Small bodies cool faster than large bodies because the ratio of surface area to volume is higher. Heat from the interior has a shorter path to the surface and escapes more readily. At Pluto's size and Pluto's distance from the Sun, approximately 5.9 billion kilometers on average, receiving roughly 900 times less solar energy per square meter than Earth, the expectation was a world whose interior had frozen solid billions of years ago, whose surface had been unmodified for geological ages, except by the slow accumulation of impact craters from the bombardment that continues throughout the solar system. Instead, New Horizons showed a surface with regions almost completely devoid of impact craters, a surface being actively modified. A surface young enough in geological terms that the expected craters have not had time to accumulate. The most dramatic evidence of this youth is Sputnik Planitia, the western lobe of the heart-shaped feature now officially named Tombaugh Regio, after Pluto's discoverer. Sputnik Planitia is a vast flat plain of nitrogen ice, approximately 900,000 square kilometers in area, roughly the size of Texas and California combined. Its surface shows almost no impact craters. The absence of craters means the surface is young. Very young by solar system standards. Estimates based on the expected flux of impacting objects in the Kuiper Belt suggest the surface of Sputnik Planitia is no more than a few million years old. In a solar system that is 4.6 billion years old, a surface that is a few million years old is geologically newborn. It has been reset, renewed, within a period of time that represents approximately 0.1% of the age of the solar system. What is renewing it? What is producing this extraordinary youth is convection. The nitrogen ice of Sputnik Planitia is convecting. It is circulating. Warmer ice from lower in the nitrogen ice layer rises toward the surface, spreads outward, cools, and sinks back down along the edges of convective cells, exactly as hot water circulates in a pot approaching boiling, exactly as rock circulates in Earth's mantle, driving plate tectonics. The evidence for this convection is visible in the images. Sputnik Planitia is divided into polygonal cells, irregular polygons with widths of roughly 10 to 40 kilometers, separated by darker troughs. The pattern is unmistakably the surface expression of convective cells, the same geometry seen in terrestrial convection experiments, in the granulation cells visible on the Sun's surface, in the cloud patterns above thunderstorms. Each polygon represents one convective cell, the rising center bright, the sinking edges darker and slightly lower. One convective cycle, one complete circulation of ice from depth to surface and back, takes approximately 500,000 to several million years, depending on the specific viscosity of nitrogen ice at Plutonian temperatures and pressures. Over the history of the solar system, Sputnik Planitia has completed hundreds or thousands of these cycles, continuously stirring and renewing the surface ice, continuously erasing any impact craters that form before they can accumulate to detectable numbers. Where does the heat come from? This is the central question that Sputnik Planitia's convection raises. Convection requires a thermal gradient, warmer material at the bottom, cooler material at the top. Something must be heating the base of the nitrogen ice layer. The most plausible candidate is radiogenic heat, the heat produced by the decay of radioactive elements in Pluto's rocky core. Even a small body like Pluto contains potassium-40, uranium-238 and thorium-232 in its rock, elements whose radioactive decay produces heat continuously over billions of years. This heat slowly conducts outward through the icy mantle and eventually reaches the base of whatever surface ice layer is present. The specific amount of heat required to drive nitrogen ice convection is relatively small. Nitrogen ice has a very low melting point at approximately 63 Kelvin and convects at temperatures well below that melting point. The thermal gradient needed to drive the convection is modest enough that radiogenic heating from Pluto's rock core is a plausible source even at this distance from the Sun with no significant tidal heating. This is one of the most significant implications of the Sputnik Planitia convection. If radiogenic heat alone can drive geological activity in a body as small as Pluto, then geological activity may be possible in a much wider range of outer solar system bodies than previously assumed. The Kuiper Belt contains hundreds of thousands of objects larger than 100 kilometers in diameter. If Pluto-sized bodies can be geologically active on radiogenic heating alone, many of these objects, each containing their own complement of radioactive elements, may be similarly active. Let us now talk about the mountains of Pluto, the ice mountains rising up to 3,500 meters above the surrounding surface that appeared in the very first high-resolution images New Horizons returned. The mountains are made of water ice. This is important for chemical reasons. Nitrogen ice and methane ice, two other major components of Pluto's surface, are far too soft and plastic at Plutonian temperatures to support high mountains. Under the pressures at the base of a mountain of nitrogen or methane ice, the ice would flow, gradually sinking under its own weight, unable to maintain the sharp, steep slopes of a mountain range for geologically significant timescales. Only water ice is rigid enough at Plutonian temperatures to support steep mountainous terrain. Pluto contains a substantial fraction of water in its bulk composition, approximately 30 to 35% by mass. Most of this water is in the form of ice in the interior icy mantle. The water ice mountains visible on the surface protrude through overlying, softer, volatile ices. They float, in a sense, like icebergs in an ocean of nitrogen and methane ice, their water ice buoyant above the denser, volatile ices surrounding them. The youth of the mountains, indicated by the same crater-counting logic that reveals Sputnik Planitia's youth, is another signal of ongoing geological activity. Old mountains are worn down by meteorite bombardment and by the slow creep of ice over time. Young, sharp mountains indicate recent uplift, that internal forces have pushed the mountain ice upward recently enough that erosion processes have not yet smoothed them. The specific mechanism of this uplift is debated. One hypothesis involves the crystallization of a subsurface ocean, liquid water slowly freezing as the interior cools, expanding as it does so because water expands when it freezes, and this expansion pushing the overlying crustal ice upward. Whether this process is still ongoing, whether the ocean is still freezing and the crust still being uplifted, or whether the current mountains are relics of an earlier, more active episode, is not definitively resolved. Let us now talk about Pluto's atmosphere, because the existence of a Plutonian atmosphere was known before New Horizons from stellar occultation measurements, but its specific structure and character revealed by New Horizons were far more interesting than expected. Pluto's atmosphere is composed primarily of nitrogen, like Earth's atmosphere, though vastly thinner. Surface pressure is approximately 10 microbars, roughly 1/100,000th of Earth's sea level pressure. This is extraordinarily tenuous, thinner than the atmosphere of Mars by a significant factor. When New Horizons looked back at Pluto with the Sun behind it, an observational geometry called a backlit view, it photographed the atmosphere illuminated by sunlight from behind. The images were striking beyond what anyone anticipated. Pluto's atmosphere is blue, not slightly bluish, distinctly, visibly, obviously blue, similar in colour to Earth's daytime sky. The same physical process produces the blue colour on both worlds. Rayleigh scattering, the preferential scattering of shorter wavelengths of light by small particles, makes Earth's sky blue, because nitrogen and oxygen molecules scatter blue light more effectively than red. On Pluto, the scattering particles are not gas molecules, but tiny organic particles called tholins, complex organic molecules produced when nitrogen and methane react under ultraviolet irradiation. And these tholins scatter sunlight to produce a similar blue hue. The atmosphere also showed more than 20 distinct haze layers extending to altitudes above 200 kilometers. These layers are analogous to smog layers visible above cities from high altitude, stratified concentrations of particles at different heights, each layer reflecting a slightly different atmospheric condition or chemical process. Tholins settling from these haze layers also coat Pluto's surface in its non-ice regions, giving Pluto its characteristic reddish-brown tones in the darker areas. The specific reddish colour visible on Pluto's dark polar region on Charon, the large moon, and on the darker equatorial band called the Cthulhu region, is the colour of tholins accumulated over millions of years of atmospheric chemistry. The atmospheric escape rate, the rate at which Pluto's thin atmosphere bleeds off into space, was measured by the ALICE ultraviolet spectrometer and found to be approximately 10,000 times lower than pre-flyby models predicted. Pre-flyby models expected a rapidly escaping atmosphere, requiring continuous replenishment from surface ice sublimation to maintain its current state. Instead, the atmosphere escapes so slowly that it could persist over timescales much longer than the models implied, suggesting the atmospheric evolution of Pluto is significantly more complex and slower than previously thought. Let us now talk about what is perhaps the most consequential discovery hidden within the New Horizons data: the evidence for a subsurface liquid ocean inside Pluto. The evidence is indirect, but multiple independent lines of evidence point in the same direction. The first and most compelling argument comes from Sputnik Planetia's position. Sputnik Planitia is located almost exactly on the anti-Charon side of Pluto, the side permanently facing away from Charon, Pluto's largest moon. This is not coincidence. Pluto and Charon are tidally locked to each other. The same side of Pluto always faces Charon, exactly as the same side of the Moon always faces Earth. When a tidally locked body contains a region of anomalous mass, heavier than the surrounding material, that region is gradually pulled by tidal forces toward a position aligned with the tidal axis, either directly facing the tidal partner or directly opposite. Sputnik Planitia is more massive than the surrounding terrain for a specific reason. It occupies a deep impact basin and is filled with thick nitrogen ice. This extra mass pulled the basin into the anti-Charon position through a process called true polar wander. The entire body of Pluto reoriented itself over geological time to place the heavy Sputnik Planitia in its tidally favoured position. For this reorientation to have occurred, Pluto's interior must have been able to deform, must have behaved more like a fluid than a rigid solid on the timescales of the reorientation. A completely solid, frozen Pluto could not have reoriented this way. A Pluto with a layer of liquid water in its interior, a liquid layer that allows the solid outer shell to shift relative to the rocky core, could have reoriented exactly as observed. The second argument comes from the shape of Pluto itself. Pluto's deviation from a perfect sphere, the specific way it is not quite round, is sensitive to its interior structure. Models that include a subsurface liquid ocean predict a shape more consistent with observations than models of a completely solid interior. The third argument is thermal. Maintaining the convection in Sputnik Planitia requires heat flowing from Pluto's interior to the base of the nitrogen ice layer. If Pluto contains an insulating layer of liquid water between the rocky core and the icy mantle, this liquid layer would trap radiogenic heat from the rock more effectively than a solid ice mantle, producing higher temperatures at the base of the surface ice and providing more robust thermal drive for convection. The proposed liquid layer is not pure water. Pure water would freeze at the temperatures expected in Pluto's interior, but water mixed with ammonia has a significantly lower freezing point. Ammonia acts as an antifreeze. An ammonia-water mixture, a brine, could remain liquid at temperatures tens of Kelvin below pure water's freezing point. This ammonia brine, potentially 100 to several hundred kilometers thick, could persist in Pluto's interior despite the extreme cold of the outer solar system, if the radiogenic heat production from the rocky core is sufficient to maintain it above its freezing point. If Pluto has a subsurface liquid ocean, the implications extend throughout the Kuiper Belt. If a body as small as Pluto can maintain liquid water purely from radiogenic heating, without any tidal heating from a giant planet, then the potential for liquid water in the solar system is far greater than the traditional concept of a habitable zone around a star suggests. The habitable zone defines the distance range where surface temperatures allow liquid water. But subsurface oceans maintained by radiogenic heat exist independent of distance from the Sun. They depend on the body being large enough and containing enough radioactive elements, conditions that could be met by many Kuiper Belt objects. Hundreds of thousands of objects larger than 100 kilometers exist in the Kuiper Belt. If Pluto, with its subsurface ocean evidence, is representative rather than exceptional, many of these objects may similarly harbor liquid water beneath their frozen surfaces. The number of liquid water environments in the solar system could be far larger than our traditional habitable zone framework suggests. Let us now talk about Charon, Pluto's largest moon, because the New Horizons data on Charon was in some respects equally surprising as the Pluto data itself. Charon was expected to be geologically dead. It is smaller than Pluto, approximately 1,212 kilometers in diameter, compared to Pluto's 2,377. Smaller means it should have cooled faster. It has no giant planet generating tidal heat. By all expectations, Charon should be a simple, battered, ancient surface, bearing the record of billions of years of impact bombardment without modification. Instead, Charon showed significant geological complexity. The most visually striking feature is the dark reddish polar cap on Charon's north pole, a region called Mordor Macula for its ominous appearance. This dark cap is not conventional polar ice. It is not water, or nitrogen, or methane frozen in a region colder than the surrounding surface. Instead, Mordor Macula is an accumulation of Tholins, the same organic molecules that colour Pluto's dark regions. The proposed formation mechanism is remarkable. Methane from Pluto's atmosphere migrates to the polar regions of Charon during the long Plutonian winters, winters that last hundreds of years while the pole faces away from the Sun. In the extreme cold of the polar night, this methane condenses on Charon's pole. When sunlight finally returns, ultraviolet radiation processes the frozen methane, producing complex organic molecules, Tholins, that remain on the surface after the methane itself sublimates away. This is a remarkable chemical process, the atmosphere of one body supplying raw material for chemical reactions on a neighbouring body, creating organic molecules that accumulate over millions of years of orbital cycles. Mordor Macula is the visible record of this interbody chemical exchange. Charon also shows an extensive canyon system, one canyon stretching more than 1,600 kilometers across the surface and reaching depths of 9 kilometers. For comparison, the Grand Canyon in Arizona is 446 kilometers long and approximately 1.8 kilometers deep. Charon's canyons are far more extensive relative to the size of the body. These canyons are interpreted as fractures in the crust that formed as Charon's internal ocean, if it had one, early in its history, when tidal interactions with Pluto were more intense, froze and expanded. Water expands when it freezes. The expanding, freezing ocean pushed outward against the crust, fracturing it and creating the extensive canyon network visible today. Let us now talk about the blade terrain of Pluto, one of the most visually extraordinary and scientifically puzzling features revealed by New Horizons. In a region near Pluto's equator called Tartarus Montes, the New Horizons images showed something that looked like a field of vertically oriented blades of ice, sharp ridged structures rising several hundred meters above the surrounding surface, oriented approximately north-south, giving the landscape an appearance of a massive bed of serrated knives. These structures are methane ice penitentes, a specific type of ice erosion feature previously known only from Earth, where it occurs at high tropical altitudes in the form of snow and ice. On Earth, solar heating sublimes snow and ice in patterns determined by the angle of sunlight and the properties of the ice, leaving vertical ridges of undisturbed ice with sublimed troughs between them. On Pluto, the same process operates, but with methane ice rather than water ice, and with sunlight approximately 900 times less intense than on Earth. The scale difference is significant. Earth's penitentes reach maximum heights of approximately 5 meters. Pluto's methane penitentes may reach hundreds of meters. The difference in scale reflects the difference in the timescales over which the sublimation can operate. Methane ice on Pluto sublimates more slowly than snow on Earth, allowing much taller structures to develop before being eroded by other processes. The discovery of penitentes on Pluto extended the known range of this geological process from Earth alone to a second world, suggesting that sublimation-driven ice erosion may be a general process occurring wherever volatile ices are present at the surface of a body with sufficient solar irradiation, regardless of how weak that irradiation is. Let us now talk about what the ongoing analysis of New Horizons data has revealed since the flyby, about the specific papers and findings that have continued to emerge in the years and now nearly decade since the encounter. The New Horizons data was not fully transmitted back to Earth immediately after the flyby. The spacecraft stored the data on board during the encounter period, and then transmitted it gradually over the following 16 months. During this transmission period, and for years afterward, scientists continued to analyze the data at increasing levels of detail, finding features and patterns that the initial high-level analysis missed. One significant post-flyby finding was the detailed characterization of nitrogen ice flow at the margins of Sputnik Planitia. Just as water ice glaciers on Earth flow under their own weight from high elevation accumulation areas toward lower elevation outlet areas, nitrogen ice in Sputnik Planitia flows outward from the central thick accumulation toward the margins of the basin. The flow patterns, visible as streaks and textures in the high-resolution images, indicate that glacial transport of nitrogen ice is an active, ongoing process reshaping the boundaries of the plain. Several features visible at the margins of Sputnik Planitia are interpreted as moraine-like accumulations of material pushed or carried by the nitrogen ice flow, analogous to the ridges of rock and debris that glaciers on Earth push ahead of themselves. This glacial action is another line of evidence that Pluto's nitrogen ice system is dynamically active, not static, not frozen in place, but moving on timescales of millions of years. Another significant post-flyby finding concerns the small moon Hydra, the brightest and most reflective of Pluto's 4 small moons. Analysis of New Horizons images of Hydra found it to be one of the most reflective objects in the solar system, its surface reflecting approximately 80 to 90% of incident sunlight. This extraordinary reflectivity indicates an almost pure water ice surface, with minimal contamination by darker organic material. The high reflectivity of Hydra was unexpected. Small bodies in the outer solar system are typically darkened over time by the accumulation of organic material from space weathering processes. For Hydra to remain so reflective suggests either that it is being continuously resurfaced by fresh water ice, perhaps from impacts or from material deposited from within the Pluto system, or that it formed from unusually pure water ice that has somehow remained uncontaminated. Post-flyby analysis also refined the characterization of Pluto's complex seasonal cycle. The way the distribution of volatile ices across the surface changes in response to Pluto's position on its eccentric 248-year orbit. Pluto's axis is tilted approximately 119 degrees from perpendicular to its orbit, meaning it rotates essentially on its side, more extremely than Uranus. This extreme tilt, combined with the high orbital eccentricity, produces seasonal cycles unlike anything in the inner solar system. During Pluto's summer at the pole currently facing the Sun, the pole receiving continuous sunlight, nitrogen ice sublimates from the Sun-facing pole and is transported through the atmosphere to the winter pole, where it condenses. This polar nitrogen cycle is predicted to produce measurable changes in the distribution of nitrogen ice visible from Earth between successive oppositions. And ground-based observations since the flyby have attempted to track these changes, finding preliminary evidence that Pluto's surface is indeed changing on decadal timescales. Let us now talk about the specific question of Pluto's interior structure in more detail, about how scientists use the surface observations to constrain what lies beneath, and why the specific interior structure matters for understanding Pluto's history and potential habitability. The interior of Pluto cannot be directly observed by any flyby or orbiting spacecraft without specialized instruments. Interior structure is inferred from indirect measurements: the shape of the body, its gravitational field, the observed surface geology, and the thermal state implied by the activity we see. New Horizons was not equipped for orbital gravity mapping. That requires an orbiter, not a flyby spacecraft. But it measured Pluto's shape with high precision through stereo imaging and radio tracking. The shape of Pluto, how it deviates from a perfect sphere, carries information about its internal structure. Pluto is nearly perfectly spherical. Its polar and equatorial diameters differ by less than 1%. This near-perfect sphericity has implications. A body achieves spherical symmetry when its internal material can flow, when the interior is sufficiently plastic or liquid to redistribute itself under gravity into the lowest energy configuration, which is a sphere. For Pluto, this means at least part of its interior behaves plastically, either because it contains liquid or because its icy components are warm enough to flow slowly over geological timescales. The overall internal structure picture suggested by New Horizons data is approximately as follows. A thin, solid outer crust of water ice, perhaps a few tens of kilometers thick. Below that, a possible layer of liquid water, water saturated with ammonia to lower its freezing point, potentially 100 to several hundred kilometers thick. Below the liquid layer, a thicker mantle of water ice. At the center, a rocky core composed of silicate minerals likely containing significant amounts of radioactive elements, producing the heat that maintains the system. This structure, crust, liquid layer, ice mantle, rocky core, is strikingly similar to the structure seen in Europa and Enceladus. Both of those bodies have subsurface liquid oceans, maintained by tidal heating from their giant planet hosts. Pluto has no giant planet for tidal heating. Its only heat source is radiogenic decay in the rocky core. Yet the structure may be similar, only the heat source differs. This parallel suggests that the interior structure of liquid water-bearing icy bodies may be more universal than previously thought, that the same basic layering can develop and persist driven by different energy sources. If so, the population of liquid water environments in the solar system is even larger than the Europa and Enceladus examples alone suggest. Let us now talk about the broader lesson that Pluto teaches about the outer solar system, about what the New Horizons discoveries mean for how we understand the Kuiper Belt as a whole, and what they imply about the range of complexity possible in small icy worlds. Before the Voyager era, the outer solar system was assumed to be geologically dead beyond a certain size threshold. Only bodies large enough to retain substantial interior heat could be active, and small, icy bodies in the cold outer reaches of the solar system were assumed to be simple, frozen remnants of the early solar system, unchanged for billions of years. The Voyagers shattered this assumption for specific bodies: Io, with its intense tidal volcanism; Europa, with its young, cracked surface, implying a subsurface ocean; Triton, with its active nitrogen geysers. But these were explained as special cases requiring specific conditions: extreme tidal heating, proximity to a giant planet, that would not generalize broadly. Pluto is different. Pluto's activity cannot be attributed to tidal heating from a giant planet. Pluto's activity is driven by radiogenic heat alone, the most universal heat source available to any body that formed from the primordial solar nebula. If radiogenic heat alone can drive geological activity in a body as small as Pluto, then there is no special condition required. Any body of comparable size and composition in the Kuiper Belt is a candidate for similar activity. The Kuiper Belt contains hundreds of thousands of bodies larger than 100 kilometers, and potentially millions of smaller ones. Among the largest, Eris, Makemake, Haumea, Quaoar, Orcus, several are comparable to or larger than Pluto. If Pluto is representative rather than exceptional, each of these bodies may harbor subsurface geological activity, potential subsurface oceans, and atmospheric and surface chemistry of unexpected complexity. We have seen one of them up close. That one turned out to be far more interesting than expected. The implication for all the others we have not yet visited is obvious. This is perhaps the deepest lesson of the New Horizons encounter with Pluto. Not the specific features of Pluto itself, as extraordinary as those are, but what those features imply about the range of complexity that exists in the outer solar system in bodies we have never visited and may not visit for decades or longer. The outer solar system is not a graveyard of simple frozen remnants. It is a population of worlds, complex, geologically diverse, chemically rich worlds that we are only beginning to understand. Pluto gave us our first close look at one member of this population. What it showed us suggests that the others are equally worth looking at. The New Horizons data is still being analysed. Papers are still appearing nearly a decade after the flyby, extracting new understanding from the dataset collected during those few hours in July 2015. The richness of that dataset exceeds the resources available to fully work through it. One flyby produced more scientific questions than the planetary science community can fully resolve without returning. No return mission is currently planned or funded. Pluto waits, approximately 6 billion kilometers away, continuing its 248-year orbit, its convecting ice still circulating, its possible subsurface ocean still slowly freezing at the edges, its thin blue atmosphere still producing organic molecules that settle onto its surface. We saw it once, for a few hours, almost a decade ago. Everything we found suggested we should go back. Let us talk about what the specific instruments aboard New Horizons measured and what each measurement contributed to the picture of Pluto that emerged, because understanding how we know what we know about Pluto is as important as knowing the facts themselves. New Horizons carried 7 science instruments chosen to characterize Pluto and its system from multiple perspectives simultaneously. Each instrument operated in a different wavelength range or measured a different type of particle or field, and together they provided a multidimensional portrait of Pluto that no single instrument could have produced alone. Ralph was the primary imaging and spectroscopy instrument, the instrument responsible for the iconic color images of Pluto that became instantly recognizable after the flyby. Ralph consisted of 2 components. The multispectral visible imaging camera, MVIC, produced color images using 4 filters covering blue, red, near-infrared, and a methane-specific wavelength. By combining images taken through different filters, scientists created false color images that revealed chemical variations across the surface more vividly than natural color images could. The specific colors in these images correspond to differences in surface composition and processing history, rather than to what Pluto would look like to human eyes. The infrared spectrometer component of Ralph, LASER, the Linear Etalon Imaging Spectral Array, mapped the chemical composition of the surface by measuring how different regions reflected infrared light at hundreds of different wavelengths simultaneously. Different ices absorb and reflect infrared light at characteristic wavelengths. Nitrogen ice at specific wavelengths, methane ice at others, carbon monoxide at others, water ice at others. LASER essentially produced a chemical map of Pluto's surface, a map showing where each type of ice is concentrated and in what relative abundance. The LASER data revealed the specific distribution of ices that we now understand as fundamental to Pluto's surface processes. Methane ice concentrated at higher elevations, nitrogen ice dominating the lowlands and particularly Sputnik Planitia. Carbon monoxide concentrated within Sputnik Planitia specifically. Water ice present in the mountain regions where it protrudes through overlying volatile ices. The spatial pattern of these ices reflects the thermal and dynamical processes, seasonal transport, sublimation, condensation, glacial flow, that continuously rearrange them across the surface. ALICE was the ultraviolet spectrometer, an instrument measuring how different atmospheric gases absorb ultraviolet light at different altitudes. When New Horizons passed behind Pluto relative to the Sun, ALICE measured the ultraviolet light from the Sun as it passed through the Plutonian atmosphere. different gases at different heights absorb the light at characteristic wavelengths, allowing the identification and altitude profiling of each atmospheric component. Alice confirmed the nitrogen-dominated composition of the atmosphere and detected methane and carbon monoxide as minor components. It characterized the altitude structure of the atmosphere, the specific rate at which atmospheric density and composition change with height. And it measured the upper atmosphere, where the atmosphere transitions into escaping ions, determining the rate at which Pluto loses its atmosphere to space. The Alice measurement of atmospheric escape rate, approximately 10,000 times lower than pre-flyby predictions, was one of the most scientifically significant quantitative results from the flyby. Pre-flyby models of Pluto's atmosphere were based on theoretical calculations of how fast nitrogen molecules, moving at typical thermal speeds, could escape Pluto's weak gravity. The actual measurement revealed that these calculations significantly overestimated the escape rate, likely because the actual upper atmosphere temperature is lower than assumed, slowing the molecules and reducing the fraction able to escape. This lower escape rate means Pluto's atmosphere is more persistent and more slowly evolving than models suggested, a fundamental revision to our understanding of atmospheric dynamics on small icy bodies. REX, the radio science experiment, used the spacecraft's radio link with Earth in a specific way to probe the atmosphere and surface. When New Horizons passed behind Pluto, as seen from Earth, the radio signal transmitted from Earth passed through Pluto's atmosphere before reaching the spacecraft. The way the atmosphere modified the signal, changing its frequency through refraction, attenuating it through absorption, encoded information about atmospheric pressure and temperature at different heights. The REX occultation measurements confirmed the low surface pressure, approximately 10 microbars, and revealed the temperature structure of the lower atmosphere in detail. The lower atmosphere was colder than models predicted, approximately 70 Kelvin near the surface, and the temperature decreased with altitude more steeply than expected. This cold lower atmosphere helps explain the low escape rate. Colder gas molecules move more slowly, and fewer of them reach escape velocity. REX also measured the surface emissivity of Pluto in the radio, the efficiency with which Pluto's surface emits radio waves, providing information about surface composition and thermal properties. Comparing the radio emission from different regions of the surface revealed differences in surface composition and thermal inertia, how quickly different surface materials heat and cool in response to changing solar illumination. SWAP and PEPSI were the particle detectors, instruments measuring the energetic particles and plasma in the space around Pluto. They detected the interaction between Pluto's escaping atmosphere and the solar wind, the stream of charged particles flowing outward from the Sun at several hundred kilometers per second. The solar wind interaction with Pluto's atmosphere creates a specific structure, a region where ionized atmospheric gas accumulates and deflects the solar wind, analogous in principle to the magnetospheres of planets with magnetic fields, but driven by atmospheric ionization rather than a magnetic dynamo. SWAP and PEPSI characterized this interaction region, finding that it extends significantly further from Pluto than pre-flyby models predicted, indicating that the atmospheric ionization rate and the solar wind interaction geometry were different from what had been assumed. The specific configuration of Pluto's interaction with the solar wind is relevant for understanding atmospheric escape. The solar wind can strip ionized molecules from Pluto's upper atmosphere and carry them away, a process called ion pickup. How efficiently this happens determines in part how fast Pluto's atmosphere evolves over geological time. The SWAP and PEPSI measurements constrained this efficiency and contributed to the revised understanding of why the escape rate is so much lower than originally predicted. LORI, the Long-Range Reconnaissance Imager, was the high-resolution panchromatic camera providing the sharpest black and white images of Pluto's surface. With spatial resolution capable of resolving features approximately 80 meters across at closest approach, LORI revealed geological detail impossible to see in the color images, which traded some spatial resolution for spectral information. The LORRI images of Sputnik Planitia revealed the polygonal cell structure of the convecting nitrogen ice at sufficient resolution to characterize individual cells, their sizes, shapes, the character of the troughs between them, providing the specific measurements needed to constrain models of nitrogen ice convection. The images of the mountain regions revealed the sharp ridges and varied textures of the water ice mountains in detail that allowed interpretation of their origin and age. The images of the dark Cthulhu region revealed complex texture within the organic-rich terrain, evidence of geological processes even in this apparently older, darker terrain. SDC, the Student Dust Counter, was built and is operated by students at the University of Colorado and measures the flux of dust particles striking the spacecraft. SDC operated throughout the journey to Pluto, characterizing the dust environment of the outer solar system and Kuiper Belt along New Horizons' trajectory. The dust measurements are relevant for understanding the bombardment environment of outer solar system bodies, the flux of small impactors that slowly resurface and modify these bodies over geological time. Let us now talk about what the specific discovery of convection in Sputnik Planitia implies for the long-term thermal evolution of Pluto, about what models of Pluto's interior history suggest happened in the past, and what is likely happening now. The heat flowing through the nitrogen ice of Sputnik Planitia and driving its convection must ultimately come from Pluto's rocky core. Uranium, thorium, and potassium-40 in the rock decay continuously, producing heat at a rate that was higher in the early solar system, when shorter-lived radioactive isotopes also contributed, and has declined over time as those isotopes were exhausted. In the earliest period of Pluto's history, the first few 100 million years after formation, radiogenic heating was substantially more intense than today. The heat production may have been sufficient to melt significant fractions of Pluto's ice, producing a global liquid water ocean shortly after formation. This early ocean would have been extensive, potentially thousands of kilometers in diameter, and warm enough to drive vigorous convection and geological activity at the surface. As Pluto cooled, the ocean would have begun to freeze. Freezing, starting from the outside, the coldest regions first, progressing inward as the interior temperature dropped. Water, expanding as it froze, would have produced extensional fractures in the overlying crust, fractures potentially analogous to the canyon systems visible on Charon, and possibly similar features on Pluto, obscured by subsequent volatile ice deposition. The question of whether Pluto's ocean has completely frozen, or whether a residual liquid layer persists today, is exactly the question that motivates the subsurface ocean hypothesis. The evidence we have discussed, Sputnik Planitia's tidal alignment, the shape measurements, the thermal requirements for convection, is consistent with a residual liquid layer. But it is not definitive proof. Recent thermal models, computational simulations of Pluto's interior temperature evolution over 4.5 billion years, suggest that a residual liquid ocean is plausible if the ammonia content of the water is sufficient to suppress the freezing point by tens of Kelvin. With a few percent ammonia by mass, the freezing point of the water-ammonia mixture drops enough that the current radiogenic heat production from Pluto's core might be sufficient to maintain a layer of liquid. Without ammonia, or with too little ammonia, the ocean would likely have completely frozen by now. Ammonia is expected to be present in Pluto. It is a common component of outer solar system ices and would have been incorporated into Pluto during its formation. But the exact ammonia content of Pluto's interior is not known. This is one of the key parameters that a future orbiter mission would constrain. By measuring Pluto's gravity field and tidal response to Charon's gravity, the interior structure can be characterized well enough to determine whether a liquid layer is present and approximately how thick it is. Let us now talk about the chemical significance of Pluto's tholins and what they represent for our understanding of the organic chemistry of the early solar system. Tholins are complex organic molecules produced when mixtures of nitrogen, methane, and sometimes water ice are irradiated by ultraviolet light or energetic particles. The name was coined by Carl Sagan and Bishan Kare in 1979 to describe the reddish-brown organic residues produced in laboratory experiments simulating the chemistry of Titan's atmosphere. The same chemistry produces the reddish colour of Pluto's dark terrain and of many other outer solar system bodies. Tholins are not a single specific compound. They are a heterogeneous mixture of complex organic molecules whose exact composition depends on the specific conditions under which they formed. Laboratory analysis of tholins produced under simulated Plutonian conditions, appropriate gas mixture, ultraviolet irradiation intensity, temperature, reveals that the mixture contains hundreds of distinct molecular species, including many amino acid precursors and nucleobase analogues. When tholins are hydrolyzed, when they react with liquid water, they produce amino acids and other molecules central to biochemistry as we know it. This connection between tholins and the building blocks of life has been recognized for decades and motivates ongoing interest in the organic chemistry of outer solar system bodies. On Pluto, tholins are produced continuously in the atmosphere through ultraviolet photolysis of nitrogen-methane mixtures and settle onto the surface. The dark reddish terrain of the Cthulhu region and the polar cap of Charon's Mordor macula represent accumulated tholins, deposits that have built up over millions of years of continuous atmospheric chemistry. If Pluto has a subsurface liquid ocean, and if that ocean has some connection to the surface, however indirect, the possibility exists that tholins produced at the surface could be incorporated into the ocean environment. In contact with liquid water, tholins produce amino acids. Amino acids in liquid water with an energy source, radiogenic heat from the core, hydrothermal reactions at the rock-water interface, are the basic ingredients for prebiotic chemistry, the chemistry that preceded life on Earth. This is not an argument that life exists on Pluto. It is an observation that the chemical prerequisites for prebiotic chemistry, organic molecules and liquid water, may coexist in Pluto's interior. Whether actual prebiotic chemistry is occurring, and whether any such chemistry has produced self-replicating molecules in the billions of years Pluto has existed, are questions that cannot be answered without direct investigation of the subsurface environment. But the questions themselves, that they are scientifically reasonable to ask about Pluto at all, represents a fundamental shift from the pre-New Horizons view of Pluto as an obviously biologically inert frozen rock. Let us now talk about the seasonal dynamics of Pluto's surface in more detail, about how the specific combination of extreme axial tilt and high orbital eccentricity produces surface changes unlike anything seen elsewhere in the solar system. Pluto's axial tilt, approximately 119 degrees from perpendicular to its orbital plane, means it rotates essentially on its side. During northern summer, the North Pole points approximately toward the Sun and receives continuous sunlight. During northern winter, the North Pole points approximately away from the Sun and experiences continuous darkness. The duration of these polar seasons is measured in decades. Pluto's year is 248 Earth years, and each pole receives continuous sunlight for approximately a third of the orbital period. The combination of this extreme tilt with the high orbital eccentricity, the orbit ranging from 29.7 to 49.3 astronomical units, means that the intensity of sunlight during a Plutonian summer depends strongly on which part of the orbit the summer occurs at. A summer occurring near perihelion is significantly more intense than a summer occurring near aphelion, because Pluto is closer to the Sun. Currently, Pluto is moving away from perihelion. It passed perihelion in 1989 and will reach aphelion in approximately 2114. The New Horizons flyby in 2015 occurred at a point in the orbit where Pluto was receiving relatively more solar energy than it will near aphelion. Atmospheric pressure during the flyby reflected this relatively active period. Conditions will change significantly as Pluto moves toward its distant aphelion. The specific predictions of how Pluto's surface and atmosphere change over one orbital cycle involve the redistribution of nitrogen ice. At perihelion, more solar energy reaches the Sun-facing regions, sublimating more nitrogen and increasing atmospheric pressure. At aphelion, less energy arrives and more nitrogen condenses out of the atmosphere onto the surface, particularly in the polar regions experiencing their cold season. The total mass of nitrogen shuttled between atmosphere and surface over one orbital cycle is substantial, potentially involving the equivalent of tens of meters of surface ice at the poles. Over multiple orbital cycles, these seasonal nitrogen transfers build up and erode polar nitrogen caps, producing a layered stratigraphic record in the polar ice, analogous in concept to the ice cores drilled from Earth's polar ice sheets to recover climate history. The layering in Pluto's polar ice, visible in some New Horizons images as slight color variations, encodes the history of Pluto's seasonal climate over millions of years. Deciphering this climate record from the layering is one of the scientific goals that a future orbiter mission would pursue. With sustained orbital observation over months or years, long enough to see the surface change, it would be possible to characterize the current season's nitrogen redistribution and to extrapolate backward to understand how the present surface formed through the accumulated seasonal cycles of the past. Let us now talk about Pluto's place in the broader context of the Kuiper Belt and what New Horizons taught us about how to approach the diversity of objects in this unexplored region. The Kuiper Belt extends from approximately the orbit of Neptune at 30 astronomical units to roughly 50 astronomical units from the Sun. It contains the remnants of the planetesimal disk from which the solar system formed, material that was not incorporated into one of the giant planets and has been preserved in relatively pristine condition since the early solar system. The largest known Kuiper Belt objects beyond Pluto include Eris, slightly smaller than Pluto but with a density suggesting more rock content, Makemake, whose surface is covered in methane ice with a reddish hue from Tholins. Haumea, rapidly rotating with a distinctly non-spherical shape and known to have a ring system. Quaoar, recently discovered to have a ring system existing well outside its expected Roche limit. And Orcus, sometimes called the anti-Pluto because of its resonance orbit. Each of these bodies has been characterized only through telescopic observations, photometry giving rough size and albedo estimates, spectroscopy giving some surface composition information, but no resolved images showing actual surface features. We know their approximate sizes, their approximate colors, some aspects of their surface chemistry. We know almost nothing about their geology, their internal structure, their atmospheric histories, or whether they are geologically active. New Horizons showed that Pluto, the one Kuiper Belt object we have visited, is geologically active, atmospherically complex, internally structured in a way that may support liquid water, and chemically rich in organics. Whether these properties are typical or exceptional among Kuiper Belt objects of comparable size cannot be determined from the observations of one example. But the pattern from inner solar system exploration is instructive. Every world visited for the first time revealed complexity and variety not predicted from pre-encounter observations. Mars, Venus, the moons of Jupiter and Saturn, each encounter added complexity rather than confirming simple expectations. The expectation that the Kuiper Belt will be similarly surprising when its members are visited seems well founded by this historical pattern. New Horizons continued past Pluto. On January 1, 2019, it flew past Arakoth, officially designated 2014 MU69, at approximately 44 astronomical units from the Sun. Arakoth turned out to be a contact binary, two lobes that gently merged in what was described as the most primordial object yet visited, showing almost no evidence of subsequent processing. Its smooth, nearly uncratered surface, covered in reddish organics, suggested it had been preserved nearly unchanged since the early solar system, a direct sample of the building blocks from which larger Kuiper Belt objects formed. The contrast between Pluto and Arakoth encapsulates the diversity of the Kuiper Belt. Pluto, geologically active, atmospherically complex, possibly internally differentiated with a liquid ocean, and Arakoth, primordial, apparently unprocessed, a fossil of early solar system conditions, are separated by only a few astronomical units in the same general region of the solar system. One is a complex world still evolving. The other is a time capsule preserving the state of the early solar system. Between these extremes, the full population of Kuiper Belt objects almost certainly spans a range of geological complexity that we have barely begun to sample. Understanding that range, characterizing the diversity of worlds that the outer solar system contains, is one of the major scientific goals of planetary science for the coming decades. Let us now talk about the specific scientific debates that the New Horizons data generated, the questions where planetary scientists disagree and where resolving the disagreement requires either better models or new observations. The origin of Sputnik Planitia remains one of the most actively debated questions in Pluto science. The basin-like depression, the absence of a raised rim typical of impact craters, the specific size and shape. These features are generally consistent with a large impact crater, but are not unambiguously interpretable as one. Some scientists favor an impact origin, arguing that the rim was buried or erased by subsequent nitrogen ice deposition. Others argue for a non-impact origin, perhaps sublimation erosion or tectonic subsidence, noting that the basin's geometry is unusual for impacts. Resolving this question requires either detailed gravity mapping of the basin from orbit. Impact craters produce characteristic gravity anomalies related to the density structure of the target material beneath them, or high-resolution imaging of the basin margins that might reveal structural features diagnostic of impact versus non-impact origin. Neither is achievable without a return mission. The existence and properties of the subsurface ocean are similarly debated. The evidence we have discussed, the tidal alignment of Sputnik Planitia, the shape measurements, the thermal requirements for convection, is all indirect. Different scientists assign different weights to these lines of evidence and arrive at different confidence levels for the ocean's existence. Some argue the evidence is compelling. Others argue the alternative explanations, complete solid interior with specific mechanical properties, cannot be ruled out without direct measurement. The relationship between Pluto's geological activity and its thermal history is another area of ongoing debate. Models of how Pluto's interior has cooled over 4.5 billion years depend sensitively on assumptions about the starting conditions, initial temperature, initial composition, the distribution of radioactive elements that are not well constrained. Different starting conditions predict different current states, and the observed geological activity can be accommodated by a range of models predicting different specific interior configurations. This kind of ambiguity, where the observations are consistent with multiple different models and distinguishing between them requires measurements not yet made, is typical of early-stage exploration. New Horizons gave us the data to build the first generation of serious Pluto models. The next generation of models will require the next generation of data, from an orbiter that can measure the gravity field, from a surface lander that can measure seismicity, from a probe that can directly sample the atmosphere or surface. Let us now talk about the technical and scientific case for returning to Pluto, about what a future Pluto mission could accomplish, and why the scientific community considers it a priority, despite the enormous cost and difficulty. An orbiter around Pluto would transform our understanding of the system in ways the flyby could not. From orbit, the spacecraft could map the entire surface, not just the hemisphere that happened to face New Horizons during the closest approach period. Regions left poorly imaged by the flyby geometry, including the entire northern polar region and much of the far hemisphere, would be fully characterized. The gravity field of Pluto, measured from orbit, would constrain the interior structure, specifically whether a liquid layer is present and approximately how thick it is. The precision of gravity measurements possible from orbit is sufficient to distinguish between a completely solid interior and one containing a significant liquid ocean layer. This single measurement would resolve what is currently the most important open question about Pluto. Long-duration atmospheric monitoring from orbit would characterize the seasonal evolution of the atmosphere, how pressure changes as Pluto moves along its orbit, how the distribution of surface ices changes in response to changing illumination, how the layered haze structure responds to different illumination conditions. These observations require watching the atmosphere change over months to years, impossible in a flyby, straightforward from orbit. The challenge, the reason no Pluto orbiter has been built and funded, is the difficulty and expense of entering orbit around Pluto. Pluto is small and distant. Reaching it requires years of travel. Slowing down from the high approach velocity to orbital speed requires either enormous fuel reserves, adding mass that must be launched from Earth and decelerated along the entire journey, or some form of aerobraking in the thin Plutonian atmosphere, which is so thin that useful aerobraking with current technology is essentially impossible. Various concepts for a Pluto orbiter have been studied. Nuclear electric propulsion, using a fission reactor to power ion thrusters that slowly accelerate and decelerate the spacecraft over the multi-year journey, offers one approach. The slow, continuous thrust of ion propulsion could, in principle, provide the velocity change needed to enter Pluto orbit without requiring the enormous fuel tanks of conventional propulsion. The challenge is the power system. A fission reactor capable of powering ion thrusters for a decade-long mission to Pluto does not yet exist at flight-ready status. Gravity assists offer another partial solution. A well-designed trajectory using Jupiter for a gravity assist and then Pluto's own gravity in a capture maneuver can reduce the fuel needed for orbital insertion. But careful trajectory design still leaves a substantial fuel requirement that adds significantly to the mission's launch mass. The Planetary Science Decadal Survey, the document setting scientific priorities for NASA's planetary science program for the coming decade, identified the Uranus system as the highest priority for a new flagship mission. Pluto did not receive the same priority ranking. It sits in a queue behind closer and, in some respects, more immediately tractable targets. But the scientific case for returning to Pluto is strong and is only growing stronger as continued analysis of the New Horizons data reveals the depth of what remains unknown. The question is not whether a Pluto orbiter would produce transformative science. It would, unambiguously. The question is when the resources become available, and when the technical solutions to the orbital insertion problem reach flight readiness. Let us now talk about what New Horizons itself is doing now, about where the spacecraft is and what it is still accomplishing after completing its primary mission. After the Pluto flyby in 2015 and the Arrokoth flyby in 2019, New Horizons entered its extended mission phase, operating in the Kuiper Belt, making observations of Kuiper Belt objects from a distance, characterizing the Kuiper Belt environment, and potentially being targeted at additional Kuiper Belt objects if suitable targets can be identified within reach of its remaining fuel and power. New Horizons is currently at approximately 57 astronomical units from the Sun, the fifth farthest human-made object from the Sun after the two Voyagers and the two Pioneer spacecraft. Its power output is declining as the plutonium-238 in its RTG continues to decay. By the late 2030s or early 2040s, it will fall below the threshold needed to operate its science instruments, at which point the spacecraft will go silent. Until then, New Horizons continues to measure the Kuiper Belt environment, the dust density, the ultraviolet background, the energetic particle flux, providing data on this poorly characterized region of the solar system. These measurements complement those of the Voyager spacecraft, now in interstellar space, extending the in situ characterization of the outer solar system by another spacecraft in a different region and direction. The team operating New Horizons is the same community that has spent decades working toward and then analyzing the Pluto encounter. They continue to extract science from the mission, from both the archived Pluto and Arrokoth data and from the ongoing Kuiper Belt observations, while advocating for resources to pursue additional Kuiper Belt targets if trajectories allow. What New Horizons found at Pluto, this specific, extraordinary, world-changing encounter with a world we thought we understood, will continue to shape planetary science for decades. The questions it raised will motivate future missions. The discoveries it made will be built upon by scientists who were not yet born when the spacecraft was designed. This is how exploration works at its best. One encounter opens a door. What is behind the door is more surprising than anyone imagined. The surprise motivates the next encounter. The next encounter opens another door. Pluto opened a door. The door was into a Kuiper Belt full of unexpectedly complex, unexpectedly active, unexpectedly chemically rich worlds that we are only beginning to understand. What is behind the next door is waiting. Let us talk about what the specific numbers from New Horizons measurements tell us about Pluto, about the concrete quantitative results that underpin everything we have discussed and that distinguish established facts from theoretical interpretations. Pluto's diameter, 2,377 kilometers, was measured by New Horizons with a precision impossible from Earth. Before the flyby, the best Earth-based estimates of Pluto's size varied by several percent, because measuring the diameter of a tiny distant disk requires resolving it against the sky, difficult even with Hubble. The New Horizons measurement settled the question definitively, and in doing so slightly revised upward the estimated size, which in turn revised downward the estimated density. The corrected density, approximately 1.85 grams per cubic centimetre, is consistent with a mixture of roughly 60 to 70% rock and 30 to 40% water ice by mass. This composition tells us Pluto is a differentiated body. The rock has sunk to form a core, and the ice has risen to form a mantle and crust, a process that requires the interior to have been at least partially liquid at some point in the past. Surface temperature measurements from ALICE and LEISA established the temperature environment in which Pluto's chemistry operates. The mean surface temperature is approximately 44 Kelvin in the nitrogen ice regions of Sputnik Planitia, just 44 degrees above absolute zero. Darker regions reach temperatures of approximately 55 to 60 Kelvin, still extraordinarily cold, but measurably warmer because they absorb more solar radiation. The mountain regions of water ice are at intermediate temperatures. This temperature mapping is critical for understanding which ices are stable where. Nitrogen is stable at 44 Kelvin, methane is stable at somewhat higher temperatures, water ice is stable at essentially any temperature found on Pluto's surface. The atmospheric pressure measurement from REX, 10 microbars at the surface, translates to a total atmospheric mass of approximately 10 trillion kilograms. This is the total amount of nitrogen currently in gaseous form in Pluto's atmosphere. The much larger reservoir of nitrogen in the surface ice of Sputnik Planitia, estimated at trillions of kilograms, dwarfs the atmospheric inventory. The atmosphere represents only a tiny fraction of Pluto's total nitrogen budget. Most of the nitrogen is locked in the surface ice, with the atmospheric fraction representing the equilibrium vapor pressure at the current surface temperature. The escape rate of the atmosphere, measured by SWAP and PEPSI to be approximately 500 kilograms per second at most, and probably much less, tells us how fast Pluto is losing its volatiles to space. At 500 kilograms per second, Pluto would lose its entire atmospheric inventory in approximately 600 years. But since the atmosphere is replenished from surface ice as fast as it escapes, the net loss is the rate at which the combined atmosphere and surface ice system loses material to space. At the measured escape rates, this net loss is extremely slow. Pluto's nitrogen budget changes on timescales of billions of years, not thousands. The crater count on Sputnik Planitia, essentially 0 craters above detection threshold in the highest resolution LoRa images, combined with the estimated impact flux from Kuiper Belt objects, gives the maximum age of the surface. If craters of a given size form at a rate of 1 per million years, and we see none, the surface must be younger than a few million years. The specific rate of impactor flux in the Kuiper Belt is uncertain. It depends on the size distribution and orbital distribution of Kuiper Belt impactors. But even with the most optimistic impactor flux assumptions, the absence of craters implies a surface younger than approximately 10 million years. The width of the convective cells in Sputnik Planitia, ranging from approximately 10 to 40 kilometers, with an average of roughly 20 to 30 kilometers, constrains the viscosity of the nitrogen ice and the depth over which convection is occurring. Convective cell widths are related to the depth of the convecting layer by a geometric factor. In laboratory convection experiments, cells are typically about as wide as the layer is deep. If this relationship applies to Sputnik Planitia, it suggests the convecting nitrogen ice layer is roughly 10 to 30 kilometers thick. This is consistent with independent estimates of the nitrogen ice deposit thickness from the depth of the basin and the expected nitrogen inventory. The height of the water ice mountains, up to 3,500 meters, constrains the mechanical properties of the water ice and the buoyancy forces driving their uplift. Mountains of this height, in a surface gravity of approximately 0.063 g, 6.3% of Earth's surface gravity, are supported against gravitational collapse by the rigidity of the water ice. The fact that they stand, rather than flowing flat over geological time, confirms that water ice at Plutonian temperatures is mechanically rigid, consistent with laboratory measurements of water ice mechanical properties at 40 to 60 Kelvin. Let us now talk about the discovery of possible active processes that the New Horizons data revealed, beyond the convection in Sputnik Planitia, that suggest Pluto's geological activity extends across multiple regions and multiple types of processes simultaneously. One of the most intriguing potential active features revealed by New Horizons is a region of irregular terrain near the margins of Sputnik Planitia, where chunks of water ice appear to be floating in the nitrogen ice of the plain. These kilometer-scale water ice blocks, irregular in shape, some aligned in chains, resemble in some respects the icebergs that float in Earth's polar seas, except that here the dense liquid that supports the floating ice is not water but nitrogen ice that is sufficiently plastic to flow slowly like a very viscous fluid. The blocks appear to be moving. Their alignment in chains and their distribution along the margins of the plain are consistent with transport by the flow of nitrogen ice from the interior of the plain toward its edges, carrying blocks of embedded or surface water ice along with the flow. If this interpretation is correct, it means Pluto has an active process of geological transport. Rocks and ice blocks carried by flowing volatile ice, that is essentially an analogue of how glaciers on Earth carry rocks from one place to another. Another potentially active feature is a region interpreted as possible cryovolcanic constructs, dome-like structures that could represent the surface expression of cryovolcanic activity, eruptions not of molten rock, but of water-ammonia slurry from the subsurface ocean. Cryovolcanism is known to occur on Enceladus, where water erupts from the south polar vents, and is suspected on several other outer solar system bodies. On Pluto, the domes are not actively erupting during the flyby observation. No plumes were detected, but their morphology is consistent with the products of past cryovolcanic activity and potentially ongoing slow extrusion of subsurface material. The potential cryovolcanic features are located in a region called Wright Montes and Picard Montes, large mound-like structures measuring hundreds of kilometers across, with central depressions reminiscent of calderas on volcanic mountains on Earth. Their surfaces show complex texture, suggesting multiple episodes of material emplacement. If these are cryovolcanic, they represent a mechanism by which material from Pluto's subsurface, including potentially the ocean water and its dissolved organic chemistry, can reach the surface and interact with the atmospheric chemistry. If cryovolcanism is active, or has been recently active on Pluto, it provides a mechanism connecting the surface organic chemistry to the subsurface liquid environment. Material from the ocean could reach the surface, interact with the nitrogen and methane chemistry, and produce complex organic molecules that then circulate through the atmosphere and deposit across the surface. This would make Pluto a chemically coupled system, rather than separate surface and interior environments, an interconnected chemical cycle spanning from the rocky core, through the liquid ocean, through the icy crust, to the surface and atmosphere. Let us now talk about what the color patterns of Pluto's surface reveal about its geological and chemical history. Because the distribution of colors across Pluto is not random, but encodes the history of processes that have shaped the surface. The color pattern of Pluto, as revealed by New Horizons' MVIC camera, divides roughly into 3 zones. The bright nitrogen-methane carbon monoxide ice of Sputnik Planitia and surrounding regions is the brightest terrain, high albedo, reflecting most of the weak sunlight that reaches it. The intermediate terrain, mountain regions, some polar deposits, is intermediate in brightness, the water ice reflecting more than the dark terrain, but less than the highly reflective volatile ices. And the dark reddish terrain of the Cthulhu region and other dark areas is the darkest, heavily coated in tholins that absorb sunlight efficiently. The specific reddish-brown color of the tholin-rich terrain carries information about the composition and processing history of the tholins. Different precursor mixtures, different ratios of nitrogen to methane, different irradiation conditions, different temperatures, produce tholins of slightly different colors. The specific shade of red observed in Pluto's dark terrain constrains the chemistry that produced it. Comparison with laboratory experiments simulating Plutonian atmospheric chemistry, UV irradiation of nitrogen-methane mixtures at appropriate temperatures and pressures, shows reasonable agreement between the laboratory tholin colors and the colors observed on Pluto. The match is not perfect. Real planetary chemistry is more complex than any laboratory simulation, but it confirms the basic attribution of the dark terrain color to atmospheric tholin chemistry. The distribution of the dark terrain, concentrated at low to mid-latitudes in the equatorial belt rather than at the poles, reflects the seasonal redistribution of volatile ices. At the poles, volatile ices periodically accumulate as seasonal deposits, covering any underlying dark material with bright, reflective ice. At low latitudes, volatile ice deposits are thinner and less persistent. The dark, tholin-rich material is more exposed. Over millions of years, this differential deposition and sublimation creates the latitudinal pattern visible in the New Horizons images. The redness of Charon's Mordor macular polar cap, produced by the specific mechanism of methane transport from Pluto's atmosphere and UV processing on Charon's pole, is a slightly different shade of red than Pluto's own dark terrain. Laboratory simulations of the Mordor macular formation process, UV irradiation of condensed methane ice, produce tholins whose color more closely matches Mordor macula's specific hue. The slight difference in color between Pluto's dark terrain and Charon's polar cap reflects the slightly different chemistry operating in each location. Pure methane versus a nitrogen-methane mixture as the precursor. Let us now talk about what New Horizons found about the smaller moons of Pluto, Nix, Hydra, Kerberos, and Styx, and what their properties reveal about the formation history of the entire Pluto system. All 4 small moons were discovered by the Hubble Space Telescope between 2005 and 2012. Before New Horizons, they were known only as points of light in Hubble images, their sizes roughly estimated from their brightness and assumed albedo, their shapes unknown, their rotation states unknown, their surface compositions unknown. New Horizons resolved all 4 as actual objects for the first time. Hydra, the largest of the 4 at approximately 55 by 40 kilometers, was found to have an extraordinarily reflective surface, reflecting approximately 80 to 90% of incident sunlight. This high reflectivity indicates an almost pure water-ice surface, one of the most reflective surfaces in the solar system. Nix is similarly reflective. The small moons appear to be water-ice dominated, with minimal contamination by darker organic material. This high reflectivity is puzzling given that space weathering processes, cosmic ray bombardment, micrometeorite impacts, exposure to ultraviolet radiation, tend to darken surfaces over time by producing complex organic molecules. For the small moons to remain so bright, they must be either very young, freshly resurfaced by some process that removed the older, darkened material, or somehow protected from space weathering in ways that are not obvious. One proposed explanation involves ejecta from Charon. Impacts onto Charon's surface launch material at velocities that can reach escape from Charon, but that are below escape velocity from the Pluto system. This material goes into orbit around Pluto and eventually coats the small moons. If freshwater ice from Charon's interior is exposed by impacts, it could continuously refresh the surfaces of the small moons with clean ice, countering the darkening from space weathering. Whether the rate of this resurfacing is sufficient to maintain the observed high albedos depends on the impact rate and the amount of fresh ice exposed per impact, a calculation that requires better constraints on several uncertain parameters. The rotation states of the small moons were found to be chaotic, not tidally locked to Pluto as expected for small moons orbiting close to a planet. Instead, the small moons tumble irregularly. Their rotation periods and orientations change unpredictably due to the complex gravitational influences of both Pluto and Charon simultaneously perturbing them. This chaotic tumbling is predicted by orbital mechanics. The Pluto-Charon binary creates a complex gravitational environment in which the small moons cannot achieve the stable, synchronous rotation that single planet systems produce. The specific orbital configuration of the small moons, their near-resonant orbital periods, their small orbital inclinations relative to the Pluto-Charon orbital plane, is consistent with formation in the debris disk that would have been produced by the giant impact that created Charon. In this model, the small moons are essentially chips from the giant impact, fragments that did not accrete into Charon, but instead went into orbit around the Pluto-Charon system and gradually migrated to their current near-resonant orbits through gravitational interactions. The sizes and masses of the small moons, much smaller than Charon, mean they contain a relatively small fraction of the total mass of the system. Charon contains approximately 99.5% of the mass of all Pluto's moons combined. The small moons are essentially debris, residual material from the same impact that formed the dominant satellite. Their existence and properties are additional constraints on the specific geometry and energetics of that ancient impact. Let us now talk about what Pluto's discovery in 1930 and its subsequent 85 years as an unknown smudge mean in the context of what New Horizons revealed, about the specific historical irony of studying an object for nearly a century without knowing what it looks like. Clyde Tombaugh was 24 years old when he discovered Pluto on February 18, 1930, by systematically comparing photographic plates taken on different nights at the Lowell Observatory in Flagstaff, Arizona. The technique, blink comparisons, in which a device rapidly alternated between two photographs of the same sky region, allowing moving objects to appear to jump back and forth, was painstaking. Tombaugh examined millions of star images before finding the one that moved with the right velocity to be at the expected distance of a trans-Neptunian object. Tombaugh spent the rest of his long life, he died in 1997 at age 90, never knowing what Pluto looked like. The resolution necessary to see Pluto's surface was simply not achievable by any telescope built or planned during his lifetime. The best Hubble images, obtained in the 1990s and 2000s, showed a blurry disk with large-scale brightness variations, but no geological features. Tombaugh's ashes are aboard New Horizons, a small portion of his cremated remains carried on the spacecraft he never lived to see launched. As New Horizons flew past Pluto in July 2015, Tombaugh's ashes were aboard, present at the moment that finally revealed what the world he discovered actually looks like. The other members of the New Horizons team who lived through the flyby had their own versions of this experience. Years of anticipation, years of building instruments and planning observations, years of cruise through the outer solar system, and then those few hours in July 2015 when the images came back and Pluto was finally real. The emotional texture of that experience, of finally seeing something that had been an abstraction for decades, is difficult to convey, but was palpable in the public communications from the New Horizons team during and after the flyby. Principal investigator Alan Stern described the moment the first high-resolution images returned as surpassing every expectation. Not because Pluto was larger or brighter or more reflective than expected, though in some ways it was, but because it showed a world of extraordinary complexity and beauty that no model had predicted. Mountains, plains, a heart, an atmosphere glowing blue in the backlit geometry. The specific image that became the defining image of the flyby, the view of Pluto's sunlit crescent showing the heart-shaped Tombaugh Regio and the haze layers of the atmosphere illuminated from behind, was taken approximately 15 minutes after closest approach, as New Horizons looked back toward Pluto with the sun behind the spacecraft. It was not planned as a priority image, it was a late addition to the encounter sequence. The team did not know exactly what they would see. What they got was one of the most beautiful planetary images ever taken. A crescent world glowing in the backlit sunlight, with its thin blue atmosphere visible as a delicate halo around the dark limb. That image is what Pluto looks like. Not the fuzzy blob, not the statistical object, a world, with geology and atmosphere and character, a place. The 85 years between discovery and first close look are not unusual by the standards of outer solar system exploration. Uranus and Neptune have not been visited since the Voyager flybys of the 1980s and have been awaiting a dedicated orbiter for almost 40 years. The outer solar system contains many worlds known only as smudges, Eris, Makemake, Haumea, the objects of the scattered disk and inner Oort cloud that will remain smudges for decades more unless dedicated missions are sent. Pluto showed us what we are missing. Every smudge in the outer solar system is a potential world, complex, active, chemically rich, full of surprises. The universe does not make simple, boring worlds at the outer edges of solar systems. It makes the same relentless variety everywhere we look. And we have barely looked. On February 18, 1930, a 24-year-old astronomer named Clyde Tombaugh was comparing photographic plates at the Lowell Observatory in Flagstaff, Arizona, when he noticed a point of light that moved. That was all it was for 85 years, a point of light. Not a world, not a surface, not a place with mountains or plains or weather, or anything that distinguished it from the billions of other points of light in the sky. Just a moving dot, detected by a young man doing painstaking, systematic work that told us there was something out there at the edge of the solar system, but told us nothing about what that something was. Tombaugh spent the rest of his long life, he died in 1997 at the age of 90, never knowing what Pluto looked like. No telescope built during his lifetime could resolve its surface. The best images obtainable showed a blurry disk a few pixels across. He discovered a world and never got to see it. His ashes are aboard New Horizons. When the spacecraft flew past Pluto on July 14, 2015, moving at 14 kilometers per second through the Pluto system, spending a few hours in the vicinity of a world that took 9.5 years to reach, Tombaugh was there. A small portion of his cremated remains, carried in a small container attached to the spacecraft, present at the moment that finally revealed what the world he discovered actually looks like. What it looks like is this: mountains of water ice rising 3,500 meters above the surrounding surface. Sharp, young, geologically recent, evidence that something inside this small frozen world is still pushing its crust upward. A vast plain of nitrogen ice, approximately 900,000 square kilometers of it, divided into polygonal cells by the slow circulation of convecting ice from depth to surface and back, erasing every impact crater before it can accumulate, renewing the surface continuously, making it geologically younger than the dinosaurs. A thin blue atmosphere with more than 20 layers of haze extending 200 kilometers above the surface, producing organic molecules through ultraviolet chemistry that settle onto the surface and give Pluto's dark regions their characteristic reddish color. And beneath all of it, possibly, if the evidence is correctly interpreted, a layer of liquid water, maintained by the heat of radioactive decay in the rocky core, surviving in the outer darkness 5.9 billion kilometers from the Sun, not because of stellar warmth, but because of physics that operates everywhere, regardless of distance. This should not be possible. Pluto is too small, too cold, too far. Every parameter we use to predict geological activity says Pluto should be a frozen, dead, featureless remnant, a geological corpse preserved in the cold of the outer solar system for billions of years without modification. Instead, it convects. Instead, it has mountains. Instead, it has an atmosphere that is blue. Instead, it might have liquid water. The 85 years between Tombaugh's discovery and New Horizons' flyby were years in which we studied Pluto as a statistic, as a data point in orbital mechanics calculations, as a target for increasingly precise size and albedo measurements, as a subject of theoretical models predicting what it must be like based on its size and distance and composition. Those models were wrong in essentially every specific way. Not marginally wrong, not wrong in ways that required modest adjustment, wrong in the ways that produce a decade of new papers ongoing scientific debate, and the persistent recognition that we did not understand what small, icy worlds in the outer solar system are capable of. And Pluto is just one of them. The Kuiper Belt contains hundreds of thousands of objects larger than 100 kilometers in diameter. Eris, Makemake, Haumea, Quaoar, Orcus. Each of them is a smudge, known only as a point of light moving against the background stars, characterized only by the statistics of photometry and spectroscopy, never resolved into a world with actual surface features and actual geology and actual atmospheric chemistry. We know approximately how big they are, and approximately what color they are, and approximately what ices cover their surfaces. We know nothing about whether they are geologically active, nothing about whether they have subsurface oceans, nothing about whether they produce organic molecules in their atmospheres and deposit them on their surfaces, nothing about whether they have mountains or convecting plains or cryovolcanic domes. New Horizons showed us that the one we looked at closely was extraordinary. The pattern of exploration throughout the solar system, every world looked at closely, revealing complexity not predicted from afar, suggests the others will be too. We have barely looked. The data from those few hours in July 2015 is still being analysed. Nearly a decade later, papers are still appearing, models are still being refined, discoveries are still being made from a dataset collected during a brief flyby that can never be repeated. The richness of the data exceeds the resources available to fully work through it. One encounter with one world produced more science than the planetary science community has fully processed. No return mission is planned. No orbiter, no lander, no follow-up of any kind is currently funded or formally scheduled. Pluto waits, continuing its 248-year orbit, its nitrogen ice still convecting in polygonal cells, its possible ocean still slowly freezing at the edges, its thin blue atmosphere still producing organic molecules in the weak sunlight of the outer solar system, without a visitor. It has been waiting since before the first multicellular life appeared on Earth. It will keep waiting. What the latest photos from Pluto showed us, what NASA's New Horizons found when it finally reached this world that had been a smudge for 85 years, is that the solar system does not make simple, boring worlds at its edges. It makes worlds of extraordinary complexity that remain completely invisible until you go there and look. Every smudge is a potential Pluto. Every point of light moving against the background stars in some patient astronomer's photographic plates is a potential world with mountains and convecting plains and blue atmosphere and organic chemistry and liquid water hidden under frozen miles of ice. We know this now because of what New Horizons found. What we do not know, what we cannot know until we send another spacecraft, another orbiter, something that can stay and watch and measure over months and years rather than hours, is whether the ocean is real, whether the cryovolcanism is active, whether the organic chemistry of Pluto's atmosphere has been interacting with the liquid water beneath for long enough to produce something more complex than chemistry, whether Pluto is merely interesting or whether it is something more. Clyde Tombaugh discovered a point of light. It turned out to be a world. What kind of world it fully is, we are still finding out.